Hello friends, welcome back to our course on General Relativity. This is the second lecture. In this video, let's continue our discussion on special relativity. Previously, the notion of inertial observers was developed. These are observers moving at constant velocities with respect to each other. We have also worked out the Lorentz transformations that relate these observers based on the condition that they should all measure the same speed of light. This is the principle of relativity. In this lecture, let's introduce the notion of energy and momentum under this principle. Here are the references for this course. You can find the links to these books on Amazon in the description below. Let's recall some results from the last lecture. The most important one is this equation, which we call the invariance equation. This equation defines capital lambda, the Lorentz transformation between two inertial reference frames. It relates the spacetime displacements between two events measured by the inertial observers O and O'. This equation is the direct result of the invariance of the associated space-time distance, which is defined by this quadratic form, that all inertial observers must agree. Eta is a 4x4 diagonal matrix, with the signs given below. Using this invariant quantity, we are able to classify particles according to the possible space-time displacements that the particles could traverse. And because of causality, physical particles can only travel across time-like or light-like displacements, but never across a space-like displacement. This will lead to causality paradoxes, which are inconsistencies in the causes and effects of events. We have shown this in the last lecture. Check out the video in the link in the description if you are unfamiliar with these results. Now we are going to look at the trajectories of these particles and derive some useful kinematic quantities. Let's start with time-like trajectories. These are trajectories composed entirely out of time-like infinitesimal line segments. Here's how we are going to describe a trajectory in spacetime. Since a curve is basically a one-dimensional object with a single degree of freedom running along its length, let's introduce a real parameter lambda, which runs continuously along the curve. Notice that even though each point can be described by different coordinates by different reference frames, the same lambda parameter is shared by all reference frames. It is invariant. Since its only purpose is to string together all the points on the trajectory in spacetime in a continuous manner according to the right sequence, which should be independent of the coordinates used to describe each point. The trajectory is composed of infinitesimal displacements, which transform in the following way between the two coordinate systems, O and O'. And as these two coordinates are related by some inhomogeneous Lorentz transformation, since they are both inertial frames, this is equal to since the parameter lambda is invariant under the change of coordinates. This implies that the tangent of the trajectory would transform in the same way as the displacement, which is how a vector transforms as defined in the previous lecture. This gradient will be the basis for the kinematic quantities that we shall derive, which are associated with each type of trajectory, whether time-like or light-like. Let's look at the trajectory curve more closely. We can invert the relation between the time coordinate and the curve parameter, expressing lambda in terms of t. This is possible because at each instant in time, the curve can only pass through a single spatial location. That is, a particle cannot be at multiple places at the same time. Therefore, t uniquely identifies a point on the trajectory in spacetime, much like the parameter lambda. Their relation is 1-to-1 and thus invertible. Substituting this function into the spatial coordinates, we would then have the familiar way of describing a particle trajectory from Newtonian mechanics. For the case of a freely moving particle, we should recover the usual solution where the velocity of the particle is constant. Or equivalently, its acceleration is zero. This is just Newton's first law. Let's see what this equation says about lambda t and the parametric curve x lambda. Expanding out the left-hand side, everything is now in terms of lambda t and x lambda and their derivatives. This has to be zero. With this equation, we can make a choice. We can fix the second derivative of lambda with respect to t to zero. This will give the relation between lambda and t. This choice will imply that d square x d lambda square must be zero. This is our second equation. The lambda equation implies that lambda and t have a linear relation. Which means that d square t d lambda square must also be zero. Which implies these two equations can be combined into a single vector equation. Thus, for the free motion of a particle, Newton's first law, together with such a choice of lambda, will give us a parametric curve that satisfies the equation in the yellow box. A parameter that gives us an equation of this form is known as an affine parameter. Such vector equations are particularly useful since they transform linearly under Lorentz transformations. Let's verify that this second derivative is really a vector. We can express this as a limit. The second derivative can be seen as the difference between two vectors and therefore must also be a vector. The same must be true for any arbitrary derivative. Let's find a affine parameter explicitly using this equation. For time-like trajectories, the proper time of the particle is an obvious candidate since it is Lorentz invariant as lambda should. Let's check if the proper time satisfies this equation. Start by calculating the first derivative of tau with respect to t. This is just the inverse of gamma, which we have introduced in the last lecture. This gives the following second derivative. Which is equal to zero if the acceleration is zero as for free motion. Thus we have shown that the proper time is really an affine parameter. We can use the affine parameter tau for time-like trajectories in general, beyond just free motion. For light, this would not be suitable since the invariant length of light-like displacements are all zero, and the proper time would simply be a constant. A different choice of the curve parameter lambda would be required. The vector dx mu d tau is an obvious choice for a kinematic variable for time-like trajectories. This is what is known as a fall velocity, which is closely related to the familiar tree velocity, as we shall see. This fall velocity has a simple invariant length, which is just a constant. The spatial part can be rewritten using the product rule. This is the tree velocity multiplied by gamma. As we can see, the familiar tree velocity is actually wrapped up within the vector structure of the fall velocity. We shall always strive to express things in terms of vectors and tensors because they transform in a simple way under Lorentz transformations. With velocity, momentum follows by just a multiplication by the mass of the particle. This contains the tree momentum. For the spatial part, let's take the non-relativistic limit. We first rewrite this term, and expanding gamma in powers of v over c. If we keep only the leading order in v over c, gamma is approximated by 1, and we have. Thus in the limit of low velocities, the spatial part of fall momentum just reduces to the tree momentum. Let's denote this spatial part by the tree vector p. Now for the time component. This is an entirely new term introduced by relativity. But as it turns out, this is related to something more familiar. Expanding out gamma and keeping only the leading order in velocity. Here, we recognize the kinetic energy from Newtonian mechanics, half mv squared. While the first term is a new term that would be present even when the particle is at rest, this is called the rest energy. This is the famous E equals mc squared. Thus, the time component of the fall momentum also makes connection with Newtonian mechanics at low velocities and could be interpreted as the energy of the particle over c. The invariant magnitude square of the fall momentum is just that of the fall velocity multiplied by m squared. Let's denote this invariant as p squared. Again, remember that this square is merely symbolic since p squared could take a negative value. Using this last relation for p mu, p squared equals This last equation gives us the dispersion relation. It is the relation between the energy of a particle and its tree momentum. This expression for the fall momentum applies not just to a single particle, but also to systems of particles, and also particles interacting with fields, and much more general systems. It's just that for a single particle, the momentum invariant could be related to the particle's mass. There's a good reason why energy and momentum should be encapsulated within something like a vector. Notice that every component of the form momentum of an isolated system must be conserved by the conservation of energy and momentum. The initial and final form momentum of the system must be equal. This is a law of nature. Suppose this law is satisfied in the reference frame of O. By the vector nature of this equation, it will automatically be satisfied in all reference frames. This is in accordance with the principle of relativity, which does not treat any observer as special. All observers must agree on the same laws of physics. It is due to these reasons that we have the confidence to conclude, even though the definitions for energy and momentum in Newtonian mechanics differ from those of relativity at higher velocities, it is the relativistic versions that are conserved. When the forms of the equations describing the laws of physics are invariant under Lorentz transformations, like what we have here in this example, we say that they are covariant. Let's turn our attention back to the single particle, but this time, let's look at a massless particle. Since the form momentum of a particle is proportional to its mass, if we were to simply set m to 0, we would just get the trivial case of a null vector. So in order to get a finite vector, as well as preserving the direction of the vector in space-time, let's simultaneously set the proper time interval d tau to 0 as m approaches 0. D tau equals 0 corresponds to ds squared equals 0, which implies that a massless particle must also travel along a like-like trajectory. But now, the proper time would be unsuitable as a parameter for the like-like trajectory, since it would have to remain constant throughout the curve. We simply have to make some other choice of parameter. The form momentum of the particle remains proportional to its form velocity, now defined with lambda. The dispersion relation of a massless particle is obtained simply by setting m to 0 in the formula for the massive case. Since we are dealing with particles that travel at the speed of light, one can't help but compare this with a similar relation for light waves. Omega is the angular frequency, and k is the wave vector. Since omega has the units of inverse time, multiplying this relation with a constant h bar, which has units of energy times time, will give us energy, as well as momentum on the other side of the equation. Comparing this with the relation from relativity gives us two equations: the Planck's equation and the de Broglie's equation. The first came from the study of light contained in a box at thermal equilibrium by Max Planck. This is the blackbody radiation. It is observed that the energy of light within the box must necessarily come in packets that are proportional to the light's frequencies. In order to explain the light's intensity at a given temperature, these packets of energies can be interpreted as particles, now known as photons. In this relation, we see the first example of wave-particle duality, in which light has both the properties of a particle and of a wave. The left-hand side represents its particle property, while the right-hand side its wave property. The de Broglie's equation is a similar equation relating momentum and wave number. H bar is known as the reduced Planck's constant, introduced by Planck to fit with the empirical data of blackbody radiation. The wave-particle duality ultimately led to the development of quantum mechanics, which is a framework that could reconcile these two apparently contradictory descriptions. But this is a subject for another video series. See the link in the description for my series on quantum mechanics. In this series on general relativity, we are still dealing with classical physics, and all we need to know here is that the photon is a massless particle of light that travels along light-like trajectories. In the next lecture, we shall tackle the wave properties of light by deriving the Maxwell's equations. Here's a summary of our results on particles traveling along time-like or light-like trajectories. These are the only physically allowed trajectories that a particle could travel, and only a massless particle can travel along a light-like trajectory. Please note that the photon is not the only massless particle that could travel along a light-like trajectory. There could be other massless particles, but we shall often use it as the prime example. The situation is as follows. In the frame of O', a particle is observed with the form momentum P'. Suppose there is another observer O moving with respect to O' at a velocity v. What is the energy of the particle with respect to O? Let's assume that O is related to O' by purely a boost to velocity v. This corresponds to the forward velocity u' of O with respect to O'. Setting v equals 0, we should get the forward velocity of O in the rest frame of O itself. In this frame, the spatial part of the vector is 0 by definition. The boost sends it to u' in the frame of O', which should agree with the expression below. Let's quickly verify this. Using the results of the matrix elements of the boost from the last lecture, this term is given by and u' really takes the expected form. Notice that because of the minus sign of the temporal part in the Minkowski metric, minus u with the lowered index is exactly the same matrix as u with the upper index. And we could form a Lorentz invariant by contracting with P. Both of these vectors are expressed in the frame of O. This is simply C times P0. Which is precisely the energy of the particle observed by O and is what we are looking for. The invariance of the inner product means this is also equal to the contraction of the corresponding terms in the frame of O'. Thus we have arrived at the solution to our problem. Alternatively, we could get the energy of the particle observed by O by directly boosting P'. The elements of this boost form the following vector. As we can see, this is proportional to the vector minus u' with lowered index, thus recovering our result above. One could also see the above result as the projection of the forward momentum along the time axis of observer O. N0' is the unit vector along this time axis. and has a negative norm. This is the result of the signature of the Minkowski metric. Now we move on to the topic of acceleration of both objects and observers. Let's assume that a particle is being observed in some inertial frame. Given the forward velocity of the particle, it is an obvious step to take another derivative with respect to the particle's proper time and call this forward acceleration. Due to the invariance of the proper time, both of these objects are vectors under Lorentz transformations. However, even as the particle is undergoing acceleration and its forward velocity changing with tau, the constraint on the magnitude of the forward velocity, as given in the blue box, remains, due purely to the definition of tau. This has to be satisfied at all times. Let's begin with an example of constant acceleration. Suppose d square x d tau square equals a, which has 4 constant components. If we were allowed to fix all 4 components of a, however we wished, the forward velocity would then be overly constrained, since its 4 components would have to satisfy 4 equations in the red box and 1 constraint in the blue box. This would then lead to a trivial solution to our acceleration equation. It is easy to work this out explicitly to see our point. Just integrate the equation twice to get the trajectory x tau. u0 and x0 are the initial velocity and position of the particle. Now we implement the constraint in the blue box to the solution in the red box. Taking the first derivative of the time component of the expression in the red box, we have. Do the same for the spatial components. Notice that this equation actually constrains tau to a constant value. This means our trajectory has collapsed trivially to just a single point in space-time. This is what we mean by over-constraint. To avoid this scenario, we can only fix 3 components of acceleration. Let's fix the spatial ones to some constants. A0 is now a dependent variable, which value will depend on the solution of this equation. To simplify the situation, let's assume that the particle is only traveling along one direction, for example, the x-axis. Both the velocity and the acceleration are along the x-axis, therefore the particle can stay on this axis. Now there's 2 degrees of freedom, constrained by 2 equations. Again, this equation of motion of x can be solved by integrating twice. u0 and x0 are the constants of integration. If we substitute this solution into the constraint equation on the forward velocity, we have an expression of dt d tau, the time component of the forward velocity. Taking another derivative will give us d square t d tau square. This is the reason why we don't have an equation of motion for the t component. It is a dependent variable. Let's write out this equation explicitly. To keep things simple, let's set both the initial velocity and position to be 0. From this equation, we get f tau. Now we can solve this equation to get a relation between t and tau. Together with x above, we would then have the full parametric solution of the trajectory. This equation can be solved by direct integration. Let's make this change of variable to z. And using an identity of hyperbolic functions, this relation will give us d tau in terms of dz. Putting all these together, we have cos z squared can be expressed in terms of cos 2z by this identity. This can now be integrated easily. Notice that we have chosen the constants of integration such that t equals 0 when z equals 0. Furthermore, from the relation between z and tau, we have this means t equals 0 when tau equals 0. Now we can replace z with tau by using this relation. We shall not deal with this complicated expression directly, but instead we'll look at its behavior in the limit of large tau. This will help us answer an important question. Under constant acceleration, will the velocity of the particle relative to the inertial observer eventually exceed the speed of light? If so, this would violate causality. As tau approaches infinity, the second term becomes quadratic in tau. Let's look at the first term. Recall that this is z. Let's invert this relation. Expressing the hyperbolic sign in terms of exponentials, we see that tau approaches infinity exponentially as z approaches infinity. Taking log on both sides of the equation, we have Let's substitute this back into the expression for t. Notice that the second term is dominant over the first term as tau approaches infinity, since this is only logarithmic in tau. Thus t becomes quadratic in tau in the limit. We can substitute this back into the solution for the equation of motion of x. We see that the speed of the particle with respect to our inertial observer approaches the speed of light as t goes to infinity. Thus the light speed limit is respected. This is one way to treat the acceleration of a particle relative to an inertial observer. Here's an alternative way, which will give us a cleaner solution to the particle's trajectory. Let's recall the definition of the force momentum. From Newtonian mechanics, the force experienced by the particle is simply the rate of change of the spatial part of the momentum with respect to the time of the inertial observer. Writing this in terms of the derivative with respect to tau, we have Now substitute in our definition for P. Let's simplify our notations by using the dot symbol from classical mechanics for the derivatives with respect to tau. Rearranging these equations, now we shall define a new notion of constant acceleration. First, let's calculate the invariant magnitude of the forward acceleration from the definition above. But let's not forget the constraint on the forward velocity, which must always hold. These two equations are sufficient for us to solve for the particle's trajectory if the quadratic invariant of A is specified. Using this equation, we seek to replace t double dot with only the derivatives of x. First, let's differentiate this equation to get the second derivatives. Recall that t dot is just gamma, which itself is just a function of the tree velocity. Thus, rearranging this equation, we are able to express t double dot in terms of just x derivatives. We can substitute this back into the acceleration equation. Let's take a closer look at this acceleration equation. In the rest frame of the particle, the instantaneous velocity of the particle is 0. Note that this is the spatial part of the forward velocity. Therefore, the first term on the right-hand side equals 0, leaving just the second term. R labels the rest frame coordinates. This is the square of the spatial part of forward acceleration in the rest frame. The invariance of the acceleration quadratic form allows us to establish this relation between the inertial observer and the rest frame of the particle. Let's set this acceleration invariant to be constant. This is what we mean by constant acceleration in this example. This constant must also be positive, since it is equal to the square of a spatial vector. This choice is in contrast with our previous example, where it is the spatial part of the forward acceleration that is assumed to be constant. This equation for a squared gives us the acceleration equation. On the right-hand side is the acceleration constant. Together with the forward velocity constraint, these two equations will give us the particle trajectory. They will be sufficient once we assume that the particle's velocity and acceleration are always along a single axis, the x-axis, as we did before. With these equations, we are now ready to solve for the particle's trajectory. Using the velocity equation, we can express t in terms of x. Taking another derivative, we have t double dot, which we can now insert into the acceleration equation. Factoring out x double dot square on the left-hand side, this term can be simplified. This gives x double dot in terms of x dot. Let's further assume that the acceleration of the particle with respect to the inertial observer is positive. We can see this as a first-order differential equation in x dot, which suggests that we should make the following change of variable. Here's how we can understand du dx. Both u and x are functions of tau. We can invert x tau and express tau in terms of x. This means u can also be expressed as a function of x, and so we can take derivatives of u with respect to x. Using these two substitutions, we can express this equation in terms of u and x. Let's now solve this integral. Let's set the initial conditions such that both the particle's initial velocity and position are 0, which means u equals 0 when x equals 0. Note that u cannot be 0 anywhere else, since the particle is constantly accelerating in the same direction and has accelerated from 0 velocity at the position x equals 0. This condition tells us how to set the constants of integration. The integrals on both sides are quite straightforward. Notice how we have chosen the integration constant. When u equals 0, x equals 0, satisfying the initial conditions. Now let's replace u with x dot. This will give us the integral that leads to x tau. This complicated-looking term is a good choice for a variable change. Let's call this y, and replace dx with dy. This form under the square root suggests that we should make another change of variable with a hyperbolic function. Let's change variable from y to z. And use this identity for hyperbolic functions. This gives This is now a very simple integral. Let's first look at the initial conditions to help us fix the constants of integration. At tau equals 0, x equals 0, which implies y equals 1 from the first change of variable, and implies z equals 0 from the second change. Solving the integral, we have this satisfies the initial condition. Now, let's reverse the changes of variables to get x as a function of tau. Plugging both sides of this equation into the hyperbolic cosine and using the relation between y and z, we have Let's express y in terms of x using the first variable change. And rearranging this equation, we have This is one of the parametric equations that define the particle's trajectory. The other part is t as a function of tau. We can get this by using the relation in the blue box below. Recall that this comes from the velocity constraint. First, we need to calculate x dot, which we can do with the solution above. And plugging this in, we have this can be simplified by a hyperbolic identity. Solving another integral will give us t. This simple integral gives us a hyperbolic sign. This satisfies the initial condition. Thus we now have the particle's trajectory under constant acceleration. From the parametric equations, we can solve for x as a function of t. We can express this hyperbolic cosine in terms of the hyperbolic sign and substitute in the expression for t. And we have x as a function of t. This is another way of representing the particle's trajectory in the frame of the inertial observer. Let's verify again that the tree velocity of the particle with respect to the inertial observer is bound by the speed of light. We need to calculate dx dt. We could use this expression, but let's try a simpler approach using the two boxes below. dx dt is equal to the ratio of x dot and t dot, which gives the hyperbolic tangent. The bounds of this function tell us that the velocity of the particle can never exceed the speed of light. We can see this by expressing this function in terms of exponentials. As tau goes to infinity, we have this approaches the speed of light. Thus we see that even constant acceleration cannot break the light speed limit. But we can make a stronger statement than constant accelerations and extend our results to more general accelerations. Recall the definition of the form momentum of a particle. Its energy is given by Let's calculate the change of this energy with respect to the time of the inertial observer. dE dt is the power needed in order to maintain the acceleration of the particle, assuming that this acceleration is always finite. Nevertheless, the power will approach infinity if the velocity approaches the speed of light, since gamma goes to infinity. Thus, to exceed the speed of light, energy would have to be transferred to the particle at an infinite rate. As far as we can see here, the speed of light is an insurmountable physical limit. Now, we shall derive the Wigner's rotation mentioned in the last lecture. We have considered the following situation the last time when examining the addition of velocities in relativity. Observer O is boosted with respect to O prime, the velocity v, while O prime is boosted with respect to O double prime, the velocity u. What we have derived in the last lecture is this. The resulting velocity of O with respect to O double prime is given by W. We can view the situation in the reverse order. From the perspective of O, O prime is boosted to velocity minus v, while O prime itself sees O double prime boosted to velocity minus u. The velocity of O double prime with respect to O is denoted by W prime. If O and O double prime are related by a pure boost without any rotation, that is, the spatial axes of these two observers are of the same orientation, then W prime ought to be just equal to minus W. Since if O is boosted to velocity W with respect to O double prime, then O double prime should be boosted in the inverted way with respect to O, which is just a boost with minus W. This turns out not to be true if U and V are not pointing in the same direction. In such cases, as we shall demonstrate, O and O double prime are not actually related by a pure boost, but by some other Lorentz transformation. Recall that we have shown in the last lecture that any Lorentz transformation which is connected to the identity can be expressed as the composition of a boost and a rotation. So it is in this case, and this rotation is known as the Wigner's rotation. What this means is that the spatial axes of O and O double prime are rotated with respect to each other. To prove this, let's show that although W prime and minus W are not equal, their magnitude remains equal, which is what happens in a rotation. To facilitate our calculations, let's first simplify our formula for velocity addition. These gamma factors are suggesting a cancellation. We will need to modify the second term in the numerator. Now we can do the cancellation. Let's first calculate W squared. The main part of this calculation lies in taking the vector square in the numerator. Our work will be much easier if we notice that there are no cross terms, that is, the dot product of u from the first term and the bracket in the second term is 0. Thus, we only need to add the square of the first term with the square of the second term. Let's simplify this expression. Substitute in the definition of gamma. Expanding out the first term, then the second term. These two terms cancel. What remains is this. We can add a nice finishing touch by rewriting this second term in the numerator in a simpler way, even though this has no bearing on the discussion that follows. Let's do it anyway. Write u squared as a contraction of the vector u with itself with the help of the Kroneker's delta. Do the same for v squared. Now for the second term. There's a useful identity we can use for this expression within the brackets. Let's just call this the epsilon contraction identity. These Kronecker deltas can be expressed as a pair of epsilon symbols contracted through a pair of indices, leaving 4 free indices. The epsilon is the Levi-Civita symbol. Its 3 indices are totally anti-symmetric. Epsilon 1, 2, 3 is equal to 1. Switching any 2 indices will give a minus sign. We have given a proof of this identity in our course on quantum mechanics. See the link in the description. No knowledge of quantum mechanics is required to follow that particular segment. Let's apply this identity. Rearranging this expression, we have this is the definition of the cross product. This is the final touch to our calculation of W squared. From this expression of W squared, we can get the result of W prime squared by using these substitutions. We can see why these substitutions work by following the sequence of Lorentz boosts in both diagrams above. It is easy to see that by these substitutions, W prime squared is equal to W squared. This is the result we have set out to prove. The length of both vectors are the same and could be related by a rotation. We can get the vector W prime by the same substitutions in the earlier expression for W. These two vectors are not equal if the vectors u and v are not pointing in the same direction. This is not so easy to see here, but we shall show this in a more definitive way in a minute. Notice that both w and w prime are linear combinations of u and v, which means both of them lie in the plane of u and v. We can also arrive at this conclusion simply from the symmetry of the situation. Both sides of the plane defined by the vectors u and v are on equal footings. Therefore, the vectors w and w prime should not skew towards either side. We can define another reference frame O tilde, which is related to O double prime by a pure boost and is at rest with respect to O. Therefore, the spatial axes of O tilde and O double prime have the same orientation, which means the spatial vector W has the same description in O tilde. On the other hand, for the frame O, since it is related to O double prime by two successive boosts, there is an additional rotation. Here, we have drawn the spatial vector W in the frame of O with exactly the same description it had in O double prime. And minus W prime is a different spatial vector in O, as we have previously claimed. As we can see, O is rotated from O tilde by some angle phi, and so is the vector W from minus W prime. Note that the vector minus W prime, when expressed in the frame of O tilde, is just equal to W, as we have shown here, since O tilde and O double prime have the same spatial orientation. Therefore, calculating the rotation between these two vectors is equivalent to finding the rotation between the two frames O and O tilde. This is also equal to the rotation of O with respect to O double prime, since O tilde and O double prime have the same spatial orientation. This is the Wigner's rotation, and we can calculate it from the dot product between minus W prime and W, which is just W squared times cosine phi. Here, we have used the fact that the magnitude of W prime is equal to W. But rather than using this dot product relation, let's use the cross product instead, since it also carries the direction of the rotation, which is indicated by the unit vector n hat. This vector points into the screen by the right-hand rule of the cross product, as minus W prime rotates into W. This is our main result for Wigner's rotation. The magnitude of the vector in the yellow box will give us sine of the rotation angle, while its direction is the direction of the rotation. We can calculate the right-hand side of this equation from our earlier expressions of W and W prime. And also W squared. This is a straightforward but tedious calculation that we will not attempt here. What we shall do instead is to apply the result in the yellow box to a simple but useful example where the right-hand side of this equation can be calculated in a relatively painless way. But before that, here's a quick summary of what we have done. Now, let's apply our results from Wigner's rotation to accelerated observers. Here, we define an accelerated observer as a reference frame that is attached to a particle which is moving along an arbitrary trajectory and may be undergoing accelerations. Each point along the trajectory in space-time is attached a reference frame which is stationary with respect to the particle. This family of reference frames defines the particle's reference frame, which we call an accelerated observer. Let's assume that this particle is also being observed by an inertial observer, which we call the lab frame. Our task is to relate these two reference frames. Notice that we have not mentioned how the reference frames at different points of the trajectory are spatially orientated with respect to each other. This is what we shall discuss next. Let's focus on two neighboring points on the trajectory, to which are attached frames O and O prime. Let's assume that these two reference frames are separated by at most a boost without any rotation in order to preserve as much as possible the orientation of the accelerated frame along the particle's trajectory. This boost must necessarily be infinitesimal, since O and O prime are separated only by an infinitesimal displacement in space-time. They are both instantaneously stationary with respect to the particle, but may be moving with respect to each other by an infinitesimal velocity, delta v, as represented in the boost, since we have assumed that the particle could be accelerating. O prime itself is moving with velocity v with respect to the lab frame O double prime. while O, which is infinitesimally further along the trajectory, is moving with respect to the lap frame at the velocity w. Here we have a situation that is virtually identical to our previous consideration of the Wigner's rotation. We only have to make the following substitutions in order to use all our previous results. These include the formula for W, which gives the following after the substitutions. Now let's proceed to calculate the Wigner's rotation of the particle frame with respect to the lap frame due to the successive Lorentz boosts using the previous formula in the yellow box. This rotation takes place over the interval it took for the particle to increase its velocity by an infinitesimal delta v relative to its previous frame, O'. Thus this rotation is also infinitesimal. We wish to calculate the rate of rotation, which is a finite quantity, at any given instant. According to the time of which frame, this is a question we shall consider later. Now, let's calculate W squared, using the same substitutions. Notice that we have not yet made any approximations regarding the infinitesimal delta v by dropping higher order terms. As we shall see, this is a crucial step because making premature approximations at this stage will lead to serious errors later on, because we shall have to make further substitutions. Like this substitution to get W' from W. Notice that we are replacing finite terms with infinitesimal ones, and vice versa. Thus, if we have made any approximation to the expression for W, terms that are actually finite could be missing from W' by this substitution. The philosophy of this series is, we aim to do as little calculations as possible, and reusing results by the appropriate substitutions is among our basic toolkit. Only after making this substitution can we begin making approximations. Keeping only terms linear in delta v, gamma reduces to 1. These two terms cancel. Note that both W and W' are in the plane defined by the vectors v and delta v. This means when we proceed to calculate the cross product in the numerator in the yellow box, all these terms are 0. The only non-zero terms are proportional to v cross delta v. This will allow us to make great simplifications. Since such terms are already linear in delta v, we could set delta v to 0 in all their coefficients. For example, the terms in the denominators reduce to 1. Now we are ready to calculate the cross product. These terms containing delta V can be dropped. As for W squared in the denominator, we can set delta V to 0. W squared just reduces to V squared. Let's express V squared in terms of gamma, in line with the rest of the coefficient. These two expressions can now be applied to the yellow box. But first, let's take a closer look at the cross product. Let's look at the original expression of W before all the approximations. Here, we note that terms like this can be expressed as the projector along the direction of V applied to the vector delta V. This projects out the component of delta V parallel to V. Thus this term in the red box, delta V minus its component parallel to V, is just its component perpendicular to V. We wish to express this vector W as V plus some infinitesimal vector delta W in the infinitesimal limit of all deltas. It is important to note that in general, delta W is not equal to delta V, as delta V is the velocity of O relative to O prime, while delta W is the change in the velocity of the particle measured by O double prime as it made its transition from O prime to O. This transition happened over the time interval delta T double prime measured by O double prime, the lab frame, and thus the instantaneous acceleration of the particle measured by the lab frame is just delta W over this time, in the limit as the time interval goes to 0. This acceleration is thus of greater physical relevance to the lab frame. Let's identify delta W from this expression. In the infinitesimal limit of deltas, this reduces to where we have used the following approximation for the denominator. Dropping the higher order terms and retaining only the terms that are up to linear order in deltas, we have thus we have found delta W. What we are really after is the cross product of V and delta W. So the first and the last term, which are both parallel to V, drops out. The component of delta V that is perpendicular to V can also be replaced by just delta V, since its parallel component doesn't contribute anyway. Compare this with the cross product below that we are trying to calculate for the Wigner's rotation. We find an identical term. Let's make a replacement. Now we can substitute these two expressions below into the equation above to calculate the Wigner's rotation. Since this is an infinitesimal rotation over an infinitesimal time, let's replace the angle phi with its infinitesimal counterpart, delta phi. This means sine delta phi reduces to just delta phi. Putting everything together into the yellow box, we have Thus we now have the infinitesimal rotation of the frame O with respect to O tilde. Recall that O tilde is the reference frame boosted directly from the lab frame O double prime to be instantaneously at rest with the particle. O tilde is often referred to as the co-moving frame. Even though O tilde and the particle frame are stationary relative to each other and experience the same proper time, they are not the same, as the particle frame is the result of a sequence of particle rest frames that are boosted relative to each other by infinitesimal velocities, depending on the particle's acceleration in the course of its motion, while O tilde is directly related to the lab frame by a pure boost. Thus it is possible for there to be a relative rotation between the particle frame and O tilde. We are now ready to calculate the rotation rate. Let's divide both sides of this equation by delta t double prime. This minus sign can be absorbed by flipping the cross product. And we now have the rotation rate of the particle frame with respect to the lab frame. This is known as the Thomas precession. This effect will be present whenever the particle is undergoing acceleration. For our application, which we shall explain in the next lecture, it is actually more relevant to express this rotation rate in the co-moving frame instead. All we have to do is to replace the time interval dt double prime with the proper time dt tilde, which are related to each other by the following relation. Note that gamma of v approaches gamma of w in the infinitesimal limits, which is why it doesn't matter which we put in this argument. Therefore, we simply get an extra factor of gamma v. The Thomas precession will have implications on how we describe an electron that is orbiting a nucleus in an atom. This is a leading order relativistic correction, that is, to the first order in V over C. Therefore, we are ignoring the effects of time dilation, which is described by gamma. Gamma can simply be set to 1, since the velocity ratio V over C only starts to appear at the quadratic level. In such an approximation, the factors in both expressions above simply reduces to half. This is crucially important to correctly describe the spin-orbital coupling of an electron in an atom. We shall leave these terms unexplained until the next lecture. In this section, we further explain our notion of a particle frame. Here, the idea of the Fermi-Walker transport is introduced. As we have said, the particle frame is a successive sequence of inertial frames in which the particle is instantaneously at rest and are related to their neighboring frames by infinitesimal boosts. The reason why we choose these to be purely Lorentz boosts without any rotations is to preserve the orientation of the particle's spatial axis as best as possible. Let's explain what we mean. To define a suitable physical marker for the orientation of a point particle, let's assume that the particle carries with it a purely spatial vector with zero time component. This is known as the spin of the particle. For example, in the O' frame, which is the rest frame of the particle as it passes through point A in space-time, the spin is given by. The spin of a particle has an intimate connection with how the particle behaves under Lorentz transformations and can be influenced by an electromagnetic field. But for our purpose, this quantity is there purely to indicate the orientation of the particle. We shall assume that there are no electric or magnetic fields present, so basically, the spin is traveling with the particle without any interactions with external influence. Furthermore, it is also assumed that there is no gravity. That comes later. In such a situation, we require the spin of the particle to be always pointing in the same direction in the inertial frame which defines the particle frame at that particular instant. S is pointing in the same direction, also in the frame of O, which is the particle frame subsequent to O', located at point B in spacetime. A and B are separated by an infinitesimal displacement. Let's go to the frame O' and look at the spin at point B. This can be done by applying the Lorentz boost connecting O and O' to the spin at point B. The zeroth component of this transformed spin is given by and the transformed spatial part of the spin is as follows. Where, as always, gamma affects only the component parallel to the boost and leaves the perpendicular component unchanged. Again, gamma approaches 1 in the infinitesimal limit. Which means the spatial part of the spin is completely unaffected by the Lorentz boost. Comparing these two spins in the frame of O', we find that the only change comes from the temporal part. Thus, the difference between these two spins is proportional to the fall velocity of the particle at point A in the frame of O'. Since the particle is at rest in this frame, at the same time, the inner product of the spin and the fall velocity is zero. Let's use this difference in spin to express the rate of change of spin with respect to the proper time of the particle at point A in the frame of O'. In the infinitesimal limit, where B approaches A and delta V approaches 0, we have It is apparent that these two equations not only apply to the spin at point A in the frame of O', but everywhere along the trajectory with respect to the respective particle frame. Furthermore, notice that these equations are either invariant or is a vector equation, which means they also preserve their form in all inertial reference frames. That is, they are covariant. In particular, they also hold in the lab frame. Let's simply leave them as so, and go to a definite reference frame when it suits our purpose. These equations follow directly from the way we define the spin along the trajectory. This is the Fermi-Walker transport of the spin along the trajectory. This set of equations allows us to derive the Thomas precession in a different way. Let's start with the first equation. Since this must hold along the entire trajectory of the particle, the derivative with respect to the particle's proper time must also be zero. This equation relates the rate of change of the spin to the forward acceleration of the particle. Moving on to the second equation, this says that ds d tau is proportional to the forward velocity by some factor phi. Let's use this to calculate the left-hand side of our new equation. And using the invariant magnitude of the forward velocity, this is equal to Let's multiply both sides of this equation by the forward velocity. Using the equation above, the left-hand side is just equals to ds d tau. Notice that we can view this term on the left-hand side of the equation as a projector parallel to the forward velocity. This has the standard form similar to the three-velocity version. The equation above simply says that by applying the forward velocity projector on ds d tau, which is proportional to u, just gives us back the same vector. We can apply this result to the previous equation. Multiply both sides of the equation by this factor, forming the projector, and we get ds d tau on the left-hand side. As before, let's denote the forward acceleration by a. And simplify our notations by using the dot symbol for tau derivative. This allows us to calculate the rate of change of spin more directly. These are the two equations commonly used to describe the Fermi-Walker transport of spin along a particle's trajectory. However, this is not the rate we are trying to calculate. S is the spin observed in the lab frame, and this is related to the spin in the particle frame through a rotation followed by a boost. Recall that by definition, the spin is constant in the particle frame, although both the rotation and the boost could change with proper time. The co-moving frame, which is related to the particle frame by just rotation, is what we are interested in. S tilde is the spin observed in this frame, and it is the change of S tilde which describes the spin precession, since this change is a pure rotation. Our goal is to calculate the dot of S tilde. There are two things we are going to show. First is that the zeroth component of S tilde is equal to 0 at all times, while its spatial component undergoes a precession. The first statement seems obvious from definition, since S tilde is just a rotation of S bar, which has 0 time component at all times. What we will do is to show that this fact is consistent with the rate of change described by the equation above. The calculation of the precession will be less trivial. Note that although the first equation above holds all along the trajectory, even though for an accelerating particle, this is a collection of inertial frames with different velocities. The second equation describes the rate of change observed from just a single inertial frame at a single velocity. Of course, the lap frame is also an inertial reference frame. Whereas both in the co-moving frame and the particle frame, the rate of change of spin is obtained only by putting together information from more than one inertial frames, which are moving with slightly different velocities. This is the definition of a non-inertial reference frame. The following picture should clarify what we mean. To observe the spin precession in the co-moving frame O tilde, we need information of the spin at position A and position B. These correspond to different rest frames of the particle that are inertial frames traveling at different velocities with respect to the lap frame, since the particle is accelerating. Whereas the lap frame is the same inertial frame throughout, moving at a constant velocity. Thus the co-moving frame is a non-inertial reference frame, since it is a collection of frames boosted relative to the lap frame, so that their spatial axes have the same orientation as the lap frame. The particle frame is also a non-inertial reference frame, since it is at rest relative to the co-moving frame, but rotated. This is the Wigner's rotation. In the particle frame, spin is a constant spatial vector. Thus the Fermi-Walker transport equation, which applies only in an inertial reference frame, does not apply to S tilde. But this equation is applicable to spin in the lap frame. Using the relation between the lap frame and the co-moving frame, we could then find the rate of change of S tilde. The fall velocity of the particle with respect to the lap frame can be written as a boost on the fall velocity in the co-moving frame. Notice the similar boost on the left-hand side. We could invert this by applying lambda minus v on both sides of this equation. This equation gives the spin rate of change in the co-moving frame of the particle. We could remove this minus sign by shifting the time derivative to the other lambda. This comes from taking derivatives on both sides of the equation in the white box. Using this equation, it is easy to show that the zeroth component of S tilde dot is 0, as we have claimed. U tilde 0 is just c, as can be seen from the forward velocity of the particle in its rest frame. From the definition of the Lorentz boost and the expression for the forward velocity in the lab frame, we can see that this lambda dot in front is just minus 1 over c times the time derivative of the forward velocity with its index lowered. This is the result of the minus sign we have to include that comes with minus v. U dot is of course just the forward acceleration. Let's just keep this relation between lambda and the forward velocity to one side for future use. This term is just a spin in the lab frame from the definition in the yellow box. Thus we see that the time derivative of the zeroth component of S tilde is really 0. This means if we set this component to be 0 initially, it will remain 0 for all times. Now let's move on to the spatial part and show that this equation implies spin precession. On the right-hand side of this equation, in the first sum, we have omitted the 0th term, since S tilde 0 is always 0, as we have just shown. The second term on the right-hand side is also 0, since the spatial part of U tilde is 0. Let's evaluate this matrix. Let's break the sum over alpha into temporal and spatial parts. This time derivative of lambda looks familiar. Recall that for a boost, lambda I0 equals lambda 0I. This we could use the blue box. For spatial indices, it doesn't matter if we raise or lower them. Thus this term is just the spatial part of the forward acceleration. And the second lambda follows directly from the Lorentz boost. Recall the purely spatial part of the Lorentz boost. What it does is to project out the component of a spatial vector that is parallel to v and multiply by gamma, leaving the perpendicular component unchanged. What about this term? First note that the purely spatial part of the Lorentz boost is unchanged when we switch v for minus v. Before we take the time derivative, let's separate out the constant part. Which we could just drop. Let's evaluate this. Express 1 over v squared in terms of gamma. Substitute this into the expression within the bracket. And simplify. This could be expressed in terms of the spatial part of the forward velocity. From this expression, we could also extract the projector in the direction of velocity v. This will be useful in other places. We shall now focus on this product. This derivative can be evaluated in two parts. Expanding the first part further, we have deliberately grouped the terms proportional to UK together. This will greatly simplify our work when we evaluate the product above. Substitute this back into the expression above. Notice that in contracting U with the terms on the right, the only non-zero contribution comes from the projector parallel to V. The perpendicular projector vanishes under contraction with U. Furthermore, the parallel projector preserves U. So we simply multiply the term proportional to U by gamma. Whereas for the second term, both projectors will contribute. Let's simplify the terms and brackets as we did before. We can use the identity in the white box below to rewrite the projector. We can say something about this spatial contraction between A and U. If we take the time derivative of the invariant magnitude of the fall velocity, we get the result that the inner product between A and U is 0. Expanding out the inner product, we find that the spatial contraction between A and U is equal to the product A0, U0. From the definition of the fall velocity, U0 is just gamma c. Taking derivative with respect to tau, this is A0. Therefore A0, U0 is just given by so the first and the third terms cancel. Let's substitute this result back into our earlier calculation. Gathering the terms multiplied by AI Uj, we have. What's left is Ui Aj. Now we are ready to substitute this matrix back into the equation for S tilde. Taking the contractions, we have the term on the right-hand side is actually equal to the cross product of S tilde with the cross product of U and A. This is the vector triple product in vector analysis. You can check out the link in the description for the Wikipedia entry. However, we can easily prove this with our old friend, the epsilon contraction formula. Just contract both sides of this identity with S tilde, U, and A. This leaves one remaining free index, which gives a vector equation. The left-hand side is our vector triple product. This is easy to recognize once you know the definition of the cross product. In terms of the epsilon symbol, this is called the Leibniz formula. On the right-hand side are just the dot product terms. Let's rearrange these cross products. To better compare with our earlier results on Thomas precession, let's write U in terms of V. We also need to express A in terms of lap frame time, T. This just involves adding a gamma factor to relate the proper time to lap time. And also this U. This is the acceleration of the particle with respect to the lap frame. Only this term contributes to the expression above, since the second term is proportional to V and vanishes under the cross product. Both of these terms are quantities measured in the lap frame. Let's denote the term in brackets as omega. Now, let's convince ourselves that this equation actually describes spin precession, where omega is the precession rate. Let the unit vector n be the axis of rotation. S is the initial spin, which ends up as S prime after some proper time interval d tau. Both are measured in the co-moving frame. Delta phi is the rotation angle. Notice that the radius of the arc traced by the tip of the spin is equal to the magnitude of n cross S tilde. This arc reduces to a line segment in the infinitesimal limit and is the change in S tilde as it rotates through an infinitesimal angle, delta phi, and this change is parallel to the tangent of the arc. This is precisely in the direction of n cross S tilde. Therefore, the change in S tilde is given by. This is how a spin changes under precession. This implies that ds tilde d tau equals omega cross S tilde. Thus the equation above does indeed describe spin precession. This omega is the Thomas precession measured in the co-moving frame and agrees with our earlier result. Since the spin is constant in the particle frame, omega is also the precession rate of the particle frame with respect to the co-moving frame.